Hello everybody, this is Dr. Pennington again, and in this video I'd like to follow up on the last video from this chapter, which talked about internal energy and what it means. So I'm not going to rehash that because you've watched that video already. What we're going to do is we're going to relate the concept of internal energy that we saw before to a new energy concept called enthalpy. And the reason we're doing this is because enthalpy is an energy term with respect to chemical reactions we're going to be studying an awful lot. Okay, the last video talked about internal energy, so it kind of makes sense for us to reroute ourselves from internal energy to enthalpy. They're both energy terms, they're both similar, but there is a subtle difference between the two. So when we talk about internal energy versus enthalpy, we're always talking about changes in internal energy, changes in enthalpy, and we talked about changes in enthalpy in internal energy in the last video. It turns out though that relating the two, they're actually very similar to each other. So a change in enthalpy for a particular reaction is equal to the change in internal energy in that particular reaction plus the product of whatever pressure and volume changes occur in that reaction. So whether pressure increases, let's say volume changes for some reason, then that's where this component comes into play. So you can see essentially calculating enthalpy, that it's a little bit more involved than when you're calculating internal energy. Now, one thing that you have seen before is this. You saw that the internal energy change for any reaction is equal to the Q, the energy change due to temperature change, heat transfer, and then W, which is work done on or by the system. Now, we're going to come back to this equation here in a minute, but when we look at this one, all right, delta H is equal to delta E plus P delta V. Most of the reactions that you guys are going to do are going to be ones you do in the lab, where the reaction is completely open to the surroundings. In other words, you do it in a, let's say you're in a reaction in a beaker, all right, and there is going to be no pressure change to speak of because your flask is open to the atmosphere, so the 1 atmosphere pressure all around it is essentially the same as what's going on in your reaction. If there was a lid on here, then of course that would be different, but there isn't. And also, when you're talking about a flask that's open to the air, you're going to be talking about very little in the way of a volume change. In fact, most of your reactions don't see much of a volume change at all. You add something to something else and something happens and volume change is negligible even if it's there. So when you have that situation where your volume change is 0, okay, then what that means, of course, is if your volume change is 0, then the product of your pressure times your volume change is also 0. Alright, and in that case, the enthalpy change for that reaction is going to be essentially equal to the internal energy change for that reaction. And this is what you're going to see for a lot of the reactions that we're going to be doing in lab. Sorry, I don't know whether you heard that or not. That was my email pinging to tell me somebody who I don't want to talk to wants to talk to me. Unless it's one of my students, of course, in which case I always want to talk to that. Okay. So at this point we can say the enthalpy change is equal to the internal energy change. But this still isn't very useful because this is not the easiest thing to measure. We want to get the enthalpy in terms of something that we can measure. I'm going to put up a formula now that you haven't seen before that actually allows you to find a way to figure out how much work is done in a reaction. You remember we said work is essentially a force acting over a distance. Work is done whenever there is either pressure change or volume change or something like that. So you can calculate the work done for a reaction by looking at the external pressure and looking at the volume change in that reaction. Notice there is a negative sign here. This means that if work is done, let's make sure we're clear about this, if work is done on the system, alright, the system being whatever it is that you're studying, if work is done on the system, if something's pushing down to the system, the volume is going to decrease. You're going to have a negative volume change because your volumes get smaller. Of course, with a negative here and a negative here, this means a positive value for the work for that process. On the other hand, if work is done by the system, in other words, the system pushing on the surroundings, alright, just imagine somebody in a box saying, help, I want to get out, I want to get out. They're going to push on the underside of that box, making the volume bigger. So therefore you have a positive volume change. Positive and a negative, of course, are a negative, and in this case you have a negative value for your work. Alright. Anyway, what we're going to do is we are going to take this formula that we had before, and I'm going to show you how we can convert it into something that we can actually work with in terms of variables that we can calculate. So we're going to take this formula again. I'm just going to write it out down here. Delta H is equal to delta E plus P delta V. Alright. Now we know we can say that our delta E, our internal energy change, is equal to the energy change due to heat transfer plus whatever work is done. Alright. I can also say that because work done is equal to the negative of P delta V, I can also say that this is true. I just switch my signs. And if I take that and plug it in here, what I get is this. Alright? And therefore this becomes Q. Now I should make a little bit of a extra addition here. I'm going to say Q sub P. If you have no volume change, you have a constant pressure. Alright? Constant pressure conditions is what the P stands for. So energy change due to temperature change at constant pressure. That's what that P means. Of course the W's cancel out here. So what we can say then is under constant, under constant pressure conditions, also implying constant volume conditions, the enthalpy change for a reaction is essentially equal to the heat transfer, the heat either gained or lost by the system. This is true for any reaction done under constant pressure conditions. Alright? Which means that any reaction you do that's open to the atmosphere, this enthalpy change is essentially equal to this. Now the reason why we're going through this is because in the next video we're going to talk about something called constant pressure calorimetry. And what calorimetry is used for is to determine the amount of energy involved when a chemical reaction occurs, whether it's exothermic or endothermic or whatever. You can use this idea of doing things at constant pressure where the volume doesn't change and the external pressure doesn't change. So you figure out the temperature change in the reaction. From that you can get the heat change in the reaction, and from that you can get the enthalpy change. The next video that I'll be showing you is about constant pressure calorimetry, so check back for that one. But basically the summary is, I'm popular today. We went from internal energy that's hard to measure to enthalpy that's much easier to measure. Alright? Okay, that's it. Thank you.